Hi, I wanted to pick up where we left off last week when discussing the different types of sedimentary rocks and the environments in which they get deposited. So we finished by looking at this slide, which is just a big overview of all of the many types of environments in which sediment can accumulate. And as you already know, when sediment accumulates, it can become lithified and turned into sedimentary rock. And that can happen either above the surface of the oceans, so meaning on land, or it can happen in submarine environments or beneath the surface of the ocean. So some examples of places on land where sedimentary deposition can occur might include the fluvial environment. Okay, so fluvial environment means rivers. So in parts of river systems, like for example in the floodplain here of this river, you might deposit fine-grained clastic sediment that will turn into siltstone or shale. Sediment can also be transported by wind and deposited in the desert environment, say a low-lying desert, where it might become lithified into a sandstone that preserves big crossbeds, like we talked about last week. You can, of course, have sedimentary environments where sediment accumulates beneath the surface of the earth, or in submarine environments. Those can include fans. So a submarine fan is this wedge-shaped material here that comes out of a submarine canyon, where you might get the accumulation of turbidity flows, where you have those graded beds we talked about. You can, of course, have beach sands, so environments in the shallow oceans where sand is accumulating, where you might get ripple marks like we've discussed. Reef systems are another place where you might develop chemical sedimentary rocks, as well as biochemical sedimentary rocks and clastic sedimentary rocks. So what I'm briefly going to do here is walk you through some of these environments and discuss the different types of sedimentary rocks that might form in each. Let's start by first talking about non-marine or terrestrial depositional environments. And we'll go from kind of highest topographically or closest to the sediment source up here to kind of the farthest away down here, mainly like lakes and floodplains of rivers. In the picture on the left, you're looking at what is obviously very high, rugged, snow-capped mountains. And these mountains contain glaciers, and the glaciers are coming down the big valleys of these mountains. And glaciers are very powerful. They are sometimes miles thick, kind of like conveyor belts of ice that are capable of bulldozing and moving clastic sedimentary debris down slope very efficiently. And when glaciers do this, they tend to pick up everything regardless of grain size and just plow it down the hill, kind of like a bulldozer would. So in glacial ice, clasts of all sizes can be carried. And so therefore, a common feature of glacial sedimentary environments is something called glacial till. And glacial till is the name we give to a rock that contains a very poorly sorted mixture of gravel, sand, silt, and clay. And it usually doesn't have any kind of sedimentary structure within it, and it tells us that that material was probably bulldozed and transported by a glacier. In contrast, on the right, but we're still pretty high up in the mountains here, so maybe we're below the glacial level, but we're still up in a place where the river valleys are quite steep and the water that's running through them is moving swiftly and the sediment that's being carried is large. So you can see all of the big boulders and cobbles that are in this mountain stream here. So in mountain stream environments, water carries large clasts during floods. And typically this isn't the case during low flow conditions. So we have these big flood events in the mountains that move the big material down slope. And eventually that large material, which is so big it can't be carried otherwise, will become deposited to produce a conglomerate. So a conglomerate would be characteristic of a mountain stream environment. And I'll remind you that a conglomerate is made of very large, so gravel sized, semi-rounded, but pretty well sorted material. Now let's say that we're traveling down slope and we are at the foot of the mountain range, where the high slope side of the mountain meets the edge of a flat valley. Where that occurs, sediment that is coming down the steeply sloping river channels that drain the mountain, all of a sudden those channels lose energy. They become very flat. Okay, so imagine that you've got like something that's rolling down a steep slope. Once it hits the flat plane, it loses energy. Same thing happens with water that's coming down the river channel. And so therefore, when it hits the valley floor, all of the sediment that water was carrying gets dumped out. And it gets dumped out to form this big fan-shaped deposit that we call an alluvial fan. And alluvial fans are cone-shaped wedges of sediment that pile up where there's a rapid drop in stream velocity at a mountain front. And so alluvial fans tend to contain sandstones and sometimes conglomerates that are have medium to large size sedimentary class and that are usually poorly sorted. And typically the class are subrounded to subangular. Here's a picture of what you might imagine forming in a river environment. So now we've moved, excuse me, past our alluvial fan and out into the valley floor. And imagine that we have now a river that is draining across the valley floor. And that river is still moving material away from the mountain, so it's probably moving somewhat swiftly, but it's carrying a range of classed sizes. The coarsest material is going to be in the deepest channel, interior channel of the river, and the river might also have a floodplain where occasionally when the water levels rise, the water spills out of the channel banks and floods out onto the flatland on either side where it deposits fine-grained material. So these fine-grained beds of sand and silt and clay that's making up shale, siltstone, maybe even some fine-grained sandstone would represent a floodplain depositional environment. And cut into that floodplain depositional environment is this structure here that you can see as I'm tracing it. This, what I traced with green, is the bottom of a large channel system. And so the river channel, where the water is moving swiftly, would be this stuff in here. And that would contain coarser material because, of course, you've got water that's moving swiftly that's capable of carrying gravel and sand size material. So you can get the deposition of sandstones and maybe also conglomerates in these river channels. We've already discussed sand dunes. Okay, so lithified sand dunes can turn into sandstones with very large crossbeds, similar to what you saw in our lecture from last week in Zion National Park. And finally, if you are in a lake bed or some environment like a river floodplain where you just have standing water, so imagine there's a big flood and the river overflows its banks and kind of sloshes out onto the floodplain. It's no longer moving downhill. Instead, it's just like a muddy, swampy area where the water is standing still and the fine-grained material can settle out of it. Same deal as in lakes, where you might have just low-energy standing water out of which the really fine-grained material is allowed to settle and form like a muddy ooze at the bottom of a lake. If you ever walked out into a lake, you know exactly what I'm talking about, that disgusting feeling where the mud gets in between your toes. Ugh. But anyway, that mud, when it lithifies and turns into a sedimentary rock, will make a mudstone or a shale. Okay, what about marine depositional environments? Everything we've talked about so far are places where sedimentary rocks form on land. But what about marine environments? Okay, so once we get off of land, there's a number of different places where sediment can be deposited. It can be deposited very close to the shore, like in a beach environment, or in a place where a river meets the ocean. Where a river meets the ocean and sedimentary deposits accumulate, we call that a delta. Okay, and so a delta is analogous to an alluvial fan, but something that forms in a submarine environment. So just as an alluvial fan is a wedge-shaped accumulation of material that forms where you get the intersection of the high slope mountain stream with the flat valley floor, same deal with a delta. So here you've got the intersection of a downslope moving river channel with the ocean. And when that happens, of course, deposition is going to occur because your river is going to get way slowed down when it dumps out into the ocean. Okay, and so what you're looking at here are a sequence of sandstones that develop like so in the delta as it progrades outward toward the ocean. Go back and point out that you can also get turbidites that might form as part of these delta deposits. So sandstones and these turbidites that are the graded beds that form from the turbid flows are typical of delta environments. On the beaches, you can get typically very well-sorted, well-rounded sandstones. And this should come as no surprise because the sand that's here on the beach, all these little pieces of sand, had to have been eroded from their source and then carried to the beach by some river system and then washed around by the waves, rolled back and forth and abraded against one another until they're finally lithified and turned into a sandstone. And it's through the wave action and the fluvial transport process that the rock fragments and mineral grains become very well sorted and very well rounded. Carbonates. So we've only been talking so far about clastic sedimentary rocks, but let's not forget biochemical and chemical sedimentary rocks. These can definitely form in shallow marine environments. So carbonates, things like limestone and dolostone, they like to form in shallow, warm, oceanic conditions. So imagine like coral reefs and things like that typically rim islands around the equator. So in the Caribbean and in the equatorial Pacific, where you have these islands, you might also be forming reef systems where carbonate rocks can develop in the warm water. And the calcite and aragonite can precipitate directly out of the seawater or can be secreted by the rich marine life that exists in the reef systems. And of course, let's not ignore completely the deep oceans. So once you get past the shallow, warm parts of the ocean, where you might be making carbonate reefs or where you might be depositing beach or delta deposits, once you're in the deep ocean, most of the really large material has already been left behind. And what you have instead is the really fine-grained material that's still suspended in the water column. And eventually that fine-grained material will settle out of the water column and will find its way all the way to the bottom of the ocean, where it can accumulate to form oozes. And those oozes can be made of microscopic marine shells like you're seeing here. These are all plankton shells. Okay, and so if these plankton shells accumulate, you might get a biochemical limestone that's very fine-grained and massive. You can also get diatomaceous or diatom shells that would form the silica-rich oozes that might make chemical chert or those kinds of things. You can also get chalk from calcite shells. These are chalk cliffs that you're seeing here. So these are all features of or types of sedimentary rocks that might form in the deep marine environment. The take-home message here is that different types of sedimentary rocks accumulate in different depositional environments. Therefore, strata that are deposited along a river are different than strata that are deposited by ocean waves or glaciers or in the deep sea. So if you study sedimentary rocks at a location, you can figure out what environment existed in that locality in the past. And so that is really the power of sedimentary rocks.